So it looks like the ions are moving along a line, a Z line. Now, let's go further. The next thing to write down. When the ions are hot or excited, the Y motion remains the same, but the X motion can increase to several inches in size.
How is that possible?
That's what we're going to talk about, how that's possible. So just write that down, that the Y motion stays the same, the X motion can expand.
But there's only 4 millimeters of space, right?
Inside the trap. The ions can go through the slits outside the trap, though, and cover several inches. So you have that. So you have these numbers down in your head. So if we excite the ions, they don't look like a line anymore. What do they end up looking like? A plane, a sheet of paper. So this ion motion that looks like a line becomes a sheet of paper. But what do we never gain height on? The Y height. The Y height never increases. So this longitudinal curve goes from being like a symmetric sphere to a long line in the X dimension. Okay. Does that make sense? No. Does it make sense to you?
It makes a point. I can accept it.
Can you paraphrase what I just said? When the ions are cool, this length and this length are the same, and they're less than the size of slits.
See, but you're excited only on the x-axis?
Only on the x-axis with the excitation. So the Y stays small, the X pulls out, and it ends up looking not like a...
So it's actually going outside of the rods.
It has to, because it has to eventually get outside the rods to where the detectors are.
Right.
Okay. So we just take that shape and we pull it out.
So
okay.
The RF field so that it doesn't.
Right. Now we'll get to there. Okay. You guys with me? Now there's two more important relationships you got to be able to write down. The first one is the mass to charge ratio is inversely related to frequency of motion. This is critical. Okay. This motion's frequency, how long it takes to go from here and complete one cycle, is inversely related to mass to charge. What does this give me? Why is this important or critical? This gives me control. Every ion moves at a different frequency. This is the heart of the LTQ, is the fact that every ion moves at a different frequency. Okay. Cool. Now, an ion's kinetic energy is directly related to its displacement from the center. So ions that are doing this have low kinetic energy, medium kinetic energy, high kinetic energy.
So do they all have the same periodicity, or no? That depends on the charge.
Depends on their mass to charge. That determines their frequency. So, if an
is it not a continuous plane? Is it like?
Oh no, it's continuous. You can increase. Okay. Now, because an ion can't change frequency, but has to move over a larger area, it's got to cover a bigger distance in the same time. It has to move at a higher velocity. So that's where energy comes into play. Okay. So cool ions are where? At the center. As the ion heats up, he moves away from the center. Okay.
So why when the hot line ion will move away from the center?
Because if he's hot, he's got to maintain the same frequency. He's got to move faster because he's hot. So he's got to...
High kinetic energy.
High kinetic energy, right. Hot is high kinetic energy. Okay. Now, these are both cause and effect. What do I mean by that? If an ion comes into the trap hot with high kinetic energy, he has a large X displacement, or net Y displacement. And the helium cools him down, and what happens when he cools? He moves to the center. So that's an effect. but I can also cause it. I can electrically pull him away from the center. And when I do that, what do I cause him to do?
Increase energy.
To increase energy, to heat up. So I can observe and I can control. Are you guys with me? This is crucial. There's a lot of information on this slide you got to understand. Now, what is the only axis I care about?
The ejection.
The x-axis. That's all I care about. The y never changes. I don't care about the y. All I care is that the y remains small, because what do the ions have to do? Get through the slit without hitting the walls. In the z, I don't care where they are in the z, because the slit runs the full length of the rods.
Do you guys remember the picture?
This only means the ion will only move in the x-axis direction.
Oh no, it's moving with the x-axis and the y.
And y.
But the y we don't care about. It's so small, it doesn't affect anything.
This y still
Because you're only exciting
Right.
on the x-axis. So the thing that causes it to spread out on the x-axis is your input of RF field.
Right. Okay.
How to give energy to the ion?
Okay, now you got to be a lot louder. Say it again.
How to put the energy on?
Ah, we'll get there. We'll get there. Okay. Okay. And then, just as we talked about, the helium is there to cool the ions by lowering their kinetic energy and bringing them to the center, axializing or cooling the ions. Okay, now. So far, what it is, we drop the front, the ions come in, we raise the front back up, and then we let them sit there for 30 milliseconds and do what? Cool, and then stabilize. And they can sit doing that forever. We've had them in the trap for I think a month and a half or something. They're just sitting there perfectly fine. We eject them, they're all there. Okay. Now, the following pictures are not in your book. Okay. They'll be in your PowerPoint. You can have them. Okay, so you can take a few notes on this one. The problem came in that for the last 2 years of the LTQ's life, we've been teaching the same theory that we taught for the LCQ and said it was analogous, which is a total load of crap because there's no connection between the two, really. Okay, so finally about 6 months ago or 7 months ago, me, Eric, and Tony, the three guys in Florida who teach this, we said to San Jose, we said, we got to know really what the theory is because this analogy is not good enough. Well, the reason we found out they hadn't been talking about the theory was because they really didn't know it. They built this instrument empirically, and you talked to the three guys who designed the instrument, and they had three totally different ideas about how it worked. So the five of us got together 2 days in San Jose. This involved some food and some beer, and we came up with the following pictures, which we are not guaranteeing to be correct, but the five main people in thermo who teach the trap or develop the trap all agree on these pictures. So here's what we think. Okay. The concept of the trap goes back to the early 50s. Okay. It was developed by Wolfgang Paul. Okay. He was a theoretician. He developed the equations of motion in electrostatic fields. Okay. He developed two objects, the quadrupole rods and the ion trap. The quad rods made sense because you put a bunch of mass in the front and out came the back one mass at a time. Okay. The trap didn't make sense because Paul only knew how to trap the ions. Paul never knew how to get the ions out of the trap, okay, in an analytically useful fashion. That was developed by George Stafford in the early 80s with John Syka. Okay. Did you overlap with John?
No.
Oh, okay. No, you were never at Hunt. That was your, maybe Scott did.
But he did ET too, right?
Yes, which will hopefully will be maybe next summer.
Not for us.
We'll see.
Are they working on that?
They're working on it.
Cool.
The funny thing is, ETD was developed by Graham Cooks a long time ago. Except that everyone just assumed the damn efficiency was so bad. Why would anyone want to use it? So Hunt. Yeah, he pushed it to make it useful, and he proved you could get some good data off it if you just ignore this efficiency and just take the small data. I'm not a big lover of the technique myself, just because teaching students BY ions is enough. And now I got to teach them CZ with the charge changes. Gives me the heebie-jeebies. Okay, now When you look back at the work of Wolfgang Paul, okay, he gets a point in his equations where he can't solve them exactly. He takes a set of differentials in two dimensions, he can't solve them. So he goes back to the work of Mathieu, who in the 1800s published an algorithm how to make substitutions to fit these types of equations. Okay, the original substitutions A and Q. Okay, now because we only care about the x dimension, we always solve for A sub x and Q sub x. We never worry about the y or the z because they don't matter.
I'm sorry, can I interrupt you?
Yes.